Right, this is where we stopped on the other day. We need to continue from here. We learned about some attributes like local preference, weight, origin, next hop, behavior, next hop attribute, and MED, multi-exit discriminator. Now, how the path is selected. We just learned what those attributes are, but we did not learn when which attribute is going to be referred. When and which attribute is going to be activated. There are many attributes. How the attributes are going to impact in path selection. When there are many attributes, there should be some precedence. There should be one more important than the other one. There should be some sequence. There should be some flow in which the attributes are verified. Cannot do something like random. If there is a checklist, it should be in order. There is confusion. Right, so BGP forwarding table. What is BGP forwarding table? This is the forwarding table. This is the table. You see, to see the forwarding table, you use this command show IP BGP. And what do you see in this forwarding table? You can see for each network, the neighbors or the next hops and the path to reach the destination. Right. Now when we have multiple paths, based on the attribute that we configured, the path is going to be elected. That's what here it is saying. BGP forwarding table usually have multiple paths from where for each destination a path will be chosen. A path is selected. Only one path, a path is selected. You see, BGP selection process eliminates any multiple paths through iteration until a single path is left. So the iteration is done until you have one path as a tie break. That's what tie break is, what iteration. You got multiple paths for each network, for each destination. BGP is not at all designed to do load balancing. You should be very strong in answering someone if someone is saying, how will you do multicast, how will you do, how will you do load sharing? Everyone will ask this question in interview. Useless question actually. But everyone wants to ask you this question. And if you would show the page number in a book and say, in this book, in this page number, it is said, BGP is not designed to perform load balancing, even then they will answer, no, they will say, no, you can't do load sharing. You can't do load balancing. You are wrong. They will say this. Even if you go to Cisco's document and show BGP is not designed to perform load balancing, they will not agree. Because they are half-boiled. That's what I will say. They did not really understand the purpose of BGP. Those people who argue with you, saying, no, it can't do load balancing. No load balancing. BGP is not designed to perform any load balancing. When you have multiple paths, you cannot do load balancing like you do in EIGRP. EIGRP will do because it is designed to do load balancing. When you go and change the variants, it will do load balancing even among unequal cost load balancing. Equal cost load balancing, every routing protocol will do except BGP. For BGP, there is no metric, so there is no equal cost. BGP has got attribute. BGP is not designed to perform load balancing. And how some people claim load balancing can be done in BGP, actually they are not talking about the default behavior of BGP. They are talking about the policy. Then they have to be very clear in the question. They should ask something like this: can we tune BGP? Tune. The word tune says that you are going to break the default behavior. Can we tune BGP to do some load balancing when we have multiple paths? Of course, you can. So they don't have the difference, they don't really know the difference between tuning and default. All those people who argue with you saying, no, you are wrong. When you say BGP is not designed to perform load balancing, when they say you as a response, no, you are wrong, you can easily judge them that these people have very less knowledge on BGP. On the cake there is a cream on the top. They know only the cream level. They really do not know the real full taste of the BGP. They really don't know the purpose of BGP. If you want load balancing, you go with AUG, OSPF, blah blah blah. That's not the purpose here. The purpose here is to choose a path according to the policy. Load balancing is not the cream here. Importance in this protocol. The importance of this protocol is to pick a path as per the policy. Because we got attributes in it. So instead of testing those attribute stuff, beating around the bush on load balancing, I don't know what benefits them. They will simply argue, conflicting. Even conflicting with Cisco document, they'll talk. You can do load balancing if you are tuning it. That is manual, that's not default. It's not designed to do load balancing. So, you see, we need to be very confident in what we speak. I want you to gain confidence on this subject because this is where they are going to confuse us when it comes to BGP. Definitely they ask this question. Can we do load balancing in BGP? Can we send the traffic via multiple paths? See, it will pick one best path among multiple paths. Very clear. But if you have some policy for some destination, this is my policy, policy A. For another destination, it is policy B. Then it will eliminate all the path and pick one path for A policy, which may be this direction. And it will eliminate all the path and pick one attribute that matches this policy B, and it may be via another direction. In that way, of course, yes, the load is getting shared. But this is not default, Load balancing is not default. BGP is not designed to perform load balancing. Now, when one single path is picked up among many multiple paths from the BGP forwarding table, that picked up path, the path which is elected as per the policy, that single path, that gets promoted to the routing table manager. It is nothing but the the algorithm that manages the routing table. Now again, it is routing table manager's decision whether to accept what BGP says or to ignore what BGP says. It is the routing table manager's decision. You know about routing table, right? Routing table will have only those routes whose administrative distance is lower. So routing table manager will accept BGP route only if BGP's administrative distance for those networks less than the administrative distance of other protocol which may also have the same network. For example, IBGP and OSPF both advertise the same network. IBGP is 200 administrative distance. EBGP is 20 for EBGP, and for IBGP it is 200. Now, when there is a network called 1.1.1.1 advertised between IBGP neighbor, also advertised by OSPF between the same neighbor, the router is not going to show BGP route in the routing table because administrative distance of OSPF is only 110. So BGP is going to ignore routing table manager is going to ignore BGP's recommendation, BGP's preference, BGP's advice, BGP's prescription. It's going to only follow what OSPF says. So that is very important. We cannot simply, expect because it is BGP, it should be there. No. BGP is only a routing protocol. It is only the routing table manager who decides what to keep in the routing table. BGP, OSPF, they all can only do recommendation of path. Did you understand the paragraph, fourth paragraph? Right. So the fifth paragraph says the route from the source with low administrative distance is what installed into the routing table. To explain this, I have added few pages in the next slide, a few slides. That is not important for you. That's not for you. That's for very zero level beginners. I put some pages. What you see is Cisco's page, but what you're going to see in next three is just I added. This is Cisco page. These are all I added. So the path control is again hop by hop. Every hop, the decision is made, and one single path will be decided every hop. One hop is one autonomous system. That is very important. One autonomous system. Now here, what I am trying to show for those beginners here is, in an organization, you will be having OSPF, you'll be having RAPE, you'll be having in OSPF not so stub area, totally stub area, not just one protocol. See, simple stub. So decisions are not going to be based on your BGP forwarding table. It is based on all this consideration. You need to consider the other routing protocols. Just to say, there may be many protocols, not just BGP or OSPF. So when we have multiple routing protocol, the routing protocol only can recommend like this to the routing table manager. Now RIP also recommends route, BGP also recommends route, OSPF also recommends route, EIGRP also recommends route. It is the routing table manager who is going to decide. Individual routing protocol have got no control over what gets installed into the routing table? Routing protocol has got no control. Because it is BGP, routing protocol is not going to salute and say, Roger, sir. No. No. It's the routing table manager. So it is based on the administrative distance routing table manager is going to pick. See here, AUG route is picked, ignoring RIP and OSPF because of the administrative distance. Lower is preferred. Now, I want to go one step further. Sometime in the routing table, you will see route shown by the routing table, but there is another process again which is deciding whether to go in this link or that link. That's called switching process. What do I mean by that? So for example, say you have done an ether channel. When you have done ether channel, it's more than one physical interface binded as one virtual link. Now who decides which link will carry these packets? Not AUG. It's a switching process. Did you understand that? What I said? So, yes. Yeah. Yeah. It's not BGP, it's not, sometimes it's not even routing table. It is the switching process finally decides. Yeah. It's a switching process. So sometimes your expectation in path selection may not match. It is all because the switching process algorithm is thinking in a different way. There are a lot of switching algorithms, see, especially when you have multiple paths, equal cost multipath. There also switching process only determines which one, which link. It's not routing table. Routing table may show more than one path when you do equal cost multipathing. Isn't it? Routing table will have more than one path when you have equal cost multipathing. AIGRP, OSPF, and RIP does equal cost multipathing. But which path is determined by switching process, not by routing table. Finally, we have come to the sequence. The route selection decision process. Let us consider you have a synchronized no loop path with valid next hop. What do I mean by that? BGP routes are learned with valid next hop. That's all it means. We have a valid next hop, a reachable next hop. As a result, the route is both valid and best. Okay. So let's say we are getting route from router 2 as well as router 3. Router 1 is getting routes from router 1 as well as router 3. Router 1, sorry. Let's say there is a network here, A dot, B dot, C dot, D. And router 1 is learning from both router 2 and router 3. Both router 2 and router 3. Which one it should take? Which one it should use as an exit? Which path router 1 should decide as a path to reach ABCD? That is determined by this attribute list. Now you see, if R1 decides to go via router 3, then it is using this AS30, AS50. If it decides to go via router 2, then it is using AS20, AS30 for the same destination. For the same destination, the paths can be totally different path, no way connecting. If the decision here changes, the entire path gets changed to the destination. Now, first thing is it prefers the high weight neighbor. When there is multiple paths, here in our scenario, there is a path via router 2, there is a path via router 3. Even here, if you see, for router 2, there is a path via router 4, there is a path via router 5. Which one to take? For that, it will check which neighbor's weight is more. By default, the weight for all neighbor is same. The weight for all neighbor is same. If I would have set weight for router 2 more, I go to router 2, or best is, let's take only router 1. I want router 2 to be the path, exit point. Then I need to go to router 2 and say, hey, we have a neighbor called router 2. Whatever you learn from him, weightage is 10. The same network is also given by router 3. With router 3, we don't have any weightage set, so the default is 0. So router 1 is now deciding to go via router 2, high weightage. We learned earlier, weight is locally significant to the router. It's locally significant to the router. So wherever you configure, only there you will see the change, not on the other routers in the same autonomous system or any other autonomous system. It's only local to the router. Now let's say we don't have weight set. We did not set weight. And for some reason, by default, there should be some path, right? By default, even when you don't tune attribute, we just learned that there will be one single path. Definitely there will be one single path. Even when you don't configure attribute, BGP will go through this attribute list. There may be somewhere a tie break. Accordingly, it will pick one path. So let's say this router 3 is a winner. Maybe this attribute matched. What attribute? Oldest route from eBGP path. Meaning, before R2 learned from eBGP, R3 has already learned that network. So R3 given routes are older than R2. Both give the same route, but who gave first? R3. That is an attribute actually. That's an attribute. You're seeing here the oldest route, ninth attribute. So let's say according to the ninth attribute, because you have not configured any attributes, there should be one path with a proper reason. There should be one path with an attribute match saying because this attribute matched, because of the oldest route, I am picking router 3. So there should be one attribute to say based on this, I pick this. That is very important. Based on what? We should say that. Based on what? We should say that. Cannot blindly say it would have gone, it will take definitely router 3. How? What is the proof? What is the proof? Why should it go router 3? What is the attribute that got matched? You see? So, let us assume that R1 picked this path. But you don't like. You don't like that. Not only R1, you don't like any router going that down path. This is down path. This one is upper path. You wish to exit via upper path. All communication from this organization should go via upper path. But by default, what has happened is lower path is selected, which you don't like. So what you can do is you can go and configure this local preference, which is going to be checked after wait. Remember, the list sequence is important. If you would have set wait and attribute, wait speaks louder than wait and local preference. If you would have set wait and local preference, wait attribute speaks louder than local preference. Because wait comes first. Yeah. So now when you are going to send all the destination traffic via upper path, you need local preference, not wait. So if you would have configured wait here and there somewhere, you need to go and cancel that, because you want every router to take same path. Which path? Upper path. See, you are setting local preference. Let's say here you are setting local preference 200. The default local preference is 100. Here it is 100. Here it is 200. But here we have set wait saying this neighbor has got more weight. This neighbor has got more weight. What is the use? Will all the traffic go via upper path? No. Any traffic that is coming here will take this path. And router 3, what it will do, router 3 will say, hey, no, you need to exit via router 2. Then it will say, fine, go to router 1. Router 1 will say, no, you go via this way. Weight is high. And this router says, no, according to local preference, you need to exit via router 2. Go this way. And it's not going to go. Your ping will not be successful. That's why you should remove the wait attribute which is there in the path. If it is there in the path, this confusion will happen. If it is there in somewhere in the corner, that doesn't matter. Only those packets that comes here will be having some impact, because this is not connected to router 2 like this. So what will happen is, if it comes here, it will divert it and go or take it like this. So now what I am trying to say is, attribute sequence is important. And we need to have a proper understanding of attribute to avoid this type of problem which I was explaining you. Having weight in the path is going to confuse the decision. According to router 3 and 2, the packet should exit via router 2. But on router 1, you might have configured wait earlier and you forgot to delete, which was pointing to router 3. I have to remove that. Otherwise, you will not have the desired path. Now, yep. Yeah. 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 It's local to the AS. All these three routers belong to same AS. So when you set 200 on router 2, it is local to AS. What does that mean? This attribute information will be immediately advertised to everyone. Now everyone will know, including router 1 and 3, every router in this autonomous system, even if I have 100 router, all 100 router will immediately know. As soon as you configure it on R2, immediately the information gets spread to all 100 routers saying, oh, we all should exit only via router 2. Wherever router 2 is, that is your direction of exit. That is what happening. See, router 1, when you configure wait, router 1 ignores local preference and router 1 is saying, I'll follow wait. I give you example. R1 has got weightage 10 for this neighbor. And for this neighbor, it is default 0. R3 says we have to go via router 2. R3 will not know about this wait. Why R3 will not know about this wait? Because we configured wait where? On R1. On router 1. That information is not known to router 3. Any packet coming, router 3 will simply say we have to go via router 2. Sorry, I cannot send it to R6. We have to go via router 2. And R1 says, no, I have a local significant weight which has got more weightage than the local preference. I want to go via router 3. So it's conflicting. You see our configuration here? So understanding the attribute and sequence is more important. Knowing attribute is good, but knowing the sequence which comes first is important. That is also important. Only then we can effectively use this attribute. Otherwise, the attribute itself will screw our network. Now, only when there is a tie in the wait, the packet is going to be forwarded as per the local preference. So here there is no tie. R1 says this has got more weightage, this is less weightage. Then I don't have any tie. Then I'll send this way. It won't check. Router 1 will never check local preference. Even though we have set local preference, this guy also knows the local preference. Router 2 has got local preference of 200. It knows very well, but it won't bother. Why? Because before local preference, weight matters. It won't check the next line. If there is a tie break in the weight, why it will check the local preference? Yeah. The next one is only if there is a tie in the local preference, it will come to the origin. Reason, please. Let's assume that we did not configure weight. We did not configure local preference. So when A.A.A comes this direction as well as this direction, because there is a tie break in weight as well as local preference, it will check the next attribute, which is local origin. Earlier in our class, we learned origin code. You remember origin code? What it is? I is preferred over E is preferred over question. But this attribute that I am talking is not about this origin code. First is weight, second is local preference, third is local origin. Local originator is not this origin code. See, this origin code is different, this local origin is different. What is local origin? The one which has got the next hop 000. You see, in this example output here, this particular network is coming from this neighbor. Also, it is directly connected. See, there is no next hop, which means what? It is in the same router. That network is also on the same router, maybe on the loopback interface or some interface. Which one should prefer? Which one should the router prefer? Of course, local origin. So you see, for the local origin, what two should be a tie break? What two should be a tie? Weight and local preference, isn't it? So what this guy, Cisco does, very smart. For those next hop 000, automatically it increases the weight to 32768. We did not configure this. It's dynamically done. So that right from the very first attribute itself can decide. You understand? Very first attribute gets automatically incremented to 32768, not 0, if the next hop is 0000. See, here also you have 0000, 32768. For local network, the next hop is 000 and the weight is 32768. So that the very first attribute itself will be a match. No. You can go up to 65535. You have 16-bit. Yeah, then that will be preferred. Yeah. You can also make BGP to prefer the other, but routing table manager will not allow you. Why? Routing table manager knows that this network is directly connected on the interface. Administrative distance is 0 for it, isn't it? So there is no use again. If you try to override the default one, local origin, it's of no use. Because the routing table manager is not going to install that route into the routing table. BGP forwarding table may say best, but the routing table manager will not accept it. Okay, next. If there is tie in this, only then it will come to shortest AS path. And you know the meaning of this. Less number of hops. In our case, if you see, both the path have got same hop. Both upper path and lower path has got same number of hops. Do you agree? Yes. Though the number of routers may be more, but it won't count the number of routers, only the autonomous system. 1, 2 hops, it will find ABCD. 1, 2 hops, it will find ABCD. So if there is tie in AS path, then it will see the origin code. If this guy has done redistribution, and if this guy has advertised, yeah, then all these routers will know that I is local, I is own network. So, again, I want to remind you that this origin code is going to be effective only if there is a tie in all the above. Correct? I think you're in mute. This is going to be effective only when there is a tie in all the above. Otherwise, this is of no use again. Again, this is of no use. Got it? This is the sequence. Next, MED. Multi-exit discriminator is exchanged between the autonomous system. Now, if you want someone to reach a network here 1.1.1.1 via this way, not via this way, then you can advertise the MED 10 here. The default is 0. So they will come like this. We'll talk about that when we go there in the lab. If you don't have, you see, this is called dual homing. Between the same autonomous systems, you have 2 connections. Only then MED is possible. MED is not applicable between this. MED is applicable only between 2 autonomous systems with more than 1 connection, which is called dual homing. And if you go back to the old videos and see your previous classes, MED is well explained there. But again, I'm going to explain in the lab. Now, what if I don't have multiple connections to the same autonomous system? Then this is not applicable. It will check this one. Is any one of the neighbor EBGP and the other one is IBGP? Then it will prefer EBGP over IBGP. What is preferred? EBGP is preferred over IBGP. If one of the path is via IBGP, the path which is a tie, one path is via EBGP and another is IBGP. Which one it prefers? EBGP. What if both are IBGP? If both are IBGP, which IBGP neighbor is closest? How it knows? It checks the routing table. Maybe OSPF or something you'll be running. It checks that OSPF reachability to your IBGP neighbor. IBGP means what? Within the same autonomous system. Within the same autonomous system, you will be running some routing protocol, right? It compares the route metric. The closest means less metric. If there is tie in this, then it picks the neighbor who gave the route earlier, first, oldest route. If this is also tie, it's very rare case to be a tie. If this is a tie, then it prefers the neighbor whose router ID is lower. This is also tiebreaker, there is no possibility of two neighbor having same route ID. In case if it is there by mistake, it is going to pick the neighbor's IP address, which is smaller, lower. You understood? Can there be any tie in this? No way. No way. No two neighbors can have same IP address. No way. See, no way. No, nothing like, like you memorize that OSI layer. OSI layer, you have learned through some acronyms, right? Nothing like that for this one. But this is easy, I tell you. If you see 2-3 times, it will be in your mind. I always remember this. I have no confusion in this because I have seen repeatedly. You see, wait, local preference. This is for single route. This is for multiple route. This is local origin, and then AS path, and then origin code, and then MED, and then EBGP or IBGP, and then the closest IGP cast, oldest EBGP path, lowest neighbor IP address, means router ID, and then the IP address. See, if you ask me, I can tell you without saying. You want me to tell? I'll tell you. Attribute number 0 is like this. Make sure there is a loop-free synchronized path with proper reachable next hop. Okay, that's like attribute 0, which is not there mentioned as 0, but I always keep it as 0. And attribute 1, you should have a neighbor with high weightage to prefer. So weight, if it is a tie, then it is going to go with a neighbor whose local preference is high. Local preference is high. If local preference is also tie, then it is going to go with local origin. Local origin will have next stop 0000, so automatically weight will be 32768 for that. If there is a tie in local preference, only then it will go to, if there is tie in local origin, only then it will go to shortest AS path. Yeah. If I write like this, is this okay? Shortest AS path. And if there is tie in this shortest AS path, if both the paths are having same number of hops, only then it goes to origin code. See, origin code comes only here as a fifth attribute. And now, only when there is tie in the origin code, it comes to MED, but MED is only applicable if you have dual homing. MED, all right? And then if there is no MED applicable, then it will check whether one of the neighbor is EBGP. EBGP is preferred over IBGP. If both are IBGP, then it is going to choose the closest IGP or IBGP neighbor. And if both are having same cost, IGP cost, then it is going to pick the oldest route neighbor who gave the route much earlier than other. And then if there is tie in this, the one with the lowest router ID, this itself will break the tie. If there is for some reason two neighbors having same router ID, very rare chance, then it is going to pick the one whose IP address is lower. Neighbor's IP address is lower. That's it. Yeah, closest IGP. Yeah, correct. No, listen. We are in what class? BGP class. To reach that IBGP within an autonomous system, what cost you will be referring? The OSPF cost, isn't it? Yes or no? You're silent. You see? Closest IGP. Why? Because see, if one is EBGP, other one is IBGP, it prefers EBGP. But if this is not tie breaking, which means both are IBGP. Both are IBGP. Which IBGP I should take? The closest. The closest IBGP, how do you know? By referring into OSPF cost to that IBGP neighbor. One of the IBGP neighbor may have lowest. That's why I put IBGP there. All right. So it's very easy to remember. If you look into that 2 times, 3 times, then you will be comfortable. All right. So we are now ready for the lab. Next class, we are going to do the lab, and we'll be using this topology here. This topology here.